All right, welcome back. Oh, wake up, wake up. Let's start our afternoon session. And the speaker is Dr. Yuan Feng. Let's welcome Dr. Yuan Feng. Okay, can you hear me? If I don't use microphone. Okay, no answer, so no one hears you. I was kidding. I was kidding. You made a job. Okay, okay. From now on, I will give you 3 lectures. Each afternoon, 3 hours, and tomorrow morning, 1.5 hours. So in this lecture, I will try to review all these, I think, recent development of platform accretion, including theory and application. Theory including dynamics and radiation. So, use that microphone. Okay.
Or talk
Yeah,
about
maybe better.
yeah.
Maybe better.
A little too quiet, I think.
Okay now? Yeah, much better.
Yeah, that's fine.
Okay. So you can imagine the lecture must be quite intense because the time is quite short. The topic I try to cover is quite broad. So given this situation, in my lecture, I will try to focus only on the physics concept and the general picture, rather than give you some detailed numerical mathematics. Okay. Here is the outline of my talk I'm trying to cover. So you can see totally there are 6 chapters. But don't worry, each chapter, some chapters quite short. Okay. The first one, I will first give you a very general introduction to some basic concepts of black hole accretion, and also some general review of the black hole accretion models. And then I will begin to introduce from chapter 2, standard thin disk model and slim disk model. I put these 2 models into one chapter because both of them belong to the so-called cold accretion flow model. By cold, I will explain later. The temperature of the accretion flow is relatively not so high, typically say 10 to 6 Kelvin. Okay. Then from chapter 3, I will focus on the discussion of the hot accretion flow, including dynamics and radiation. In chapter 4, I will discuss the application of the hot accretion flow model. Application including in Sagittarius A star, which is the supermassive black hole located in our galactic center, and also some black hole X-ray binaries, especially the hot state and the quiescent state, and also some typical low luminosity AGN. Then in chapter 5 and chapter 6, these are relatively quite modern and a new field in this in black hole accretion, wind and jet, including the production mechanism of the wind and the jet, and also their main physical properties. In recent years, this community have strong interest to wind. The main reason, in my point of view, is because of the AGN feedback. Because now people generally agree AGN feedback play a crucial role in galaxy formation and evolution. So the medium for the feedback, including photons and matter including jet and wind. This is why in this community, in the recent years, we have strong interest to wind. So this is the reason why in the last chapter, I will briefly talk about AGN feedback. But I'm not sure whether I have enough time to finish, especially the last chapters. Okay. The main reference of my lecture, including these 2. One is this book. I think many of you should know this book. This is a very famous book in this field. Accretion Power in Astrophysics, published in my Cambridge University Press. This book mainly, I will use this book mainly to introduce some basic concepts and the standard thin disk model. And that's all. So for most of the part of my lecture, I will use this reference. This is the paper written by myself and also a professor in Harvard, Ramesh Narayan. This is published this year in annual review journal. Okay. This is a general review of hot accretion flow around black holes. So now let's begin from chapter 1, introduction to some basic concepts. Before I introduce the theory, let me show you some movement. This is a very typical MHD numerical simulation, black hole accretion. So a black hole is located here. At the beginning, there is a rotating torus. This is a cross section of the gas. So all these white, the yellow lines represent magnetic field lines. So once we start the simulation, we will have a so-called MMR instability, magnetorotational instability. So in this case, the angular momentum of the gas will be transferred outward, so the accretion will start. So you can see now we have a turbulence, we have jet, outflow, and accretion, everything. Okay, this is a very general picture to let you have some general ideas. So how common is accretion in the universe? So one application field is AGN, Active Galactic Nuclei. This is well known. Another one is black hole X binary. I believe John will give you some more detailed discussion about black hole X binary. The third one is gamma ray burst. This is also a very big community. Then all these three fields, central compact objects are black hole. But for some different other fields, say star formation and planet formation, it is also a process of accretion, except the central object is not a black hole, but a protostar. But the basic theory of the accretion is roughly same. And also we have cooling flow with galaxy and galaxy clusters. So you can see from this review, black hole accretion is a quite fundamental process in the universe. So first, of course, I briefly, very briefly mentioned what is black hole. So this is a prediction of general relativity. The structure of the black hole is quite simple. It composed of the event horizon, which can be regarded the surface of the black hole, and also singularity. All the matter are concentrated in this point according to GR. The effect of the black hole on the space of time can be seen from this picture. This is a picture of our galaxy. So if we put a black hole between this galaxy and our telescope, what we'll see will change into this way. Okay, this is because the change of the space around the black hole. Okay. So what is accretion? Accretion generally means means for a rotating gas. Means the gas has some angular momentum. So all this gas, the surrounding black hole, will fall into the black hole because of the strong gravity of the central object. So in this process, the gravitational energy of the gas will be converted into the thermal energy of the gas because total energy should be conserved. So this means the temperature of the gas will become higher. So in this case, the gas will, of course, emit very strong radiation. This is accretion. Two important concepts is accretion rate and radiative efficiency. So accretion rate, this is very simple. I don't need to say. So efficiency of accretion is usually defined in this way. This is the luminosity emitted by the total accretion flow. Okay. This is the accretion rate. Okay. This is the radius of the innermost circular orbit of the accretion flow. This usually is regarded as the innermost edge of the accretion flow. So the gravitational energy can release until this radius. So if we put this value, we will see the luminosity will equal to this value. Okay. This is the 1/6 is the typical efficiency of the black hole accretion. So this number is quite high, especially compared to other forms of energy production, say the chemical energy. If we burn oil or coal and so on. And even it is much higher than nuclear reaction. For nuclear reaction, the efficiency is only this value. So this number is much higher than this value. Another concept that we often see when we read the literature is thermal temperature. So what is the thermal temperature? Thermal temperature is roughly means during the accretion, roughly half of the gravitational energy will be converted into the thermal energy of the gas. The other half is still in the kinetic energy. Okay, so this is the thermal energy, the thermal temperature. Then Bondi accretion. For Bondi accretion, describe accretion of zero angular momentum. There is no rotation for the gas. So one concept is Bondi radius. So as shown by this dashed line. So Bondi radius describe the range where the black hole can control the gas accretion. So this is defined by this equation. The gravitational energy in this boundary radius is equal to the thermal energy of the gas. Within this radius, you can imagine the gravitational energy will be larger than the thermal energy. So this means the gas within this reality cannot escape or not easy to escape from the gravity of the black hole. So from this equation, we can easily derive these equations. This is the boundary radius. Okay. This is the sound speed. Denotes the thermal energy of the gas. Then accretion rate from this equation we can also easily get. This is 4 pi r squared. This means the area of this sphere. This is the typical velocity of the gas, and this is density. This is why we have such an accretion rate. Okay. So very easy. Then Eddington luminosity. Eddington luminosity is the balance when the gravitational force is equal to the radiation force. Okay. This will give us Eddington luminosity. So consider a fluid or gas element in the accretion disk. So on one hand, it will feel the gravitational force described with this equation. Okay. On the other hand, this fluid element will feel the other force. It is a radiation force. Okay. This is also easy. So this L over 4 pi r squared, this means the flux, right? Divided by C, this means the momentum flux. Okay. So this sigma means the Thomson cross section. Okay. So this means one electrons will will accept how many fraction of the momentum flux from radiation. This is by definition, this is the radiation force. Okay. This is the So I equal this and this together will give us the Eddington limit. So this means for black hole accretion, the luminosity accretion flow can reach should not be larger than this value. Otherwise, radiation force will be larger than gravitational force. Accretion will be stopped. Okay. But I want to emphasize this Eddington luminosity is only correct for spherical accretion. Once we have angular momentum, the spherical symmetry will be broken. In that case, the luminosity will be easily exceed this limit. Okay. This is one mistake many people want easily to make. Okay. Now some basic hydrodynamics and MHD. I think some of you should already know this is standard equations for hydrodynamics. This is a mass conservation. This is a momentum equation. Okay. This is acceleration. And this is the gradient of the gas pressure. This is a typical force for gas dynamics. And this term describing the gravitational force. So this is the Lagrangian derivative. Then we have energy equation. This is the specific internal energy of the gas. This is density. This is pressure. And we also, for this equation to be closed, we also have equation for state. For the MHD, the only difference compared to HD is now we have magnetic field. This is quite important because intrinsically black hole accretion can operate only because we have magnetic field. So this is quite important. So MHD is basically HD plus Lorentz force because we have magnetic field. So now we need one more equation to evolve the magnetic field. This is Faraday's law. This you should all know. For ideal MHD, the gas is a perfect electron conductor. So we have such kind of equation. Then we transform it into the lab frame. We will get the very famous induction equation. This is a very important equation for MHD.
So did you say accretion occur only because of magnetic field
Sure.
resistance?
Yes.
Why do you say so?
Because magnetic field will supply the mechanism of angular momentum transport. So for accretion to operate, we have to transport the angular momentum outward. So only magnetic field can play such a role. So for ideal MHD, we have two limits. One is strong field limit. Strong field means magnetic field pressure is much larger than the gas or thermal pressure of the gas. So in this case, the matter will be controlled by the magnetic field. Okay, this is easy to understand. Okay, one people is very strong, the other people have to follow it. Okay, so this is the strong field case. Another extreme is a weak field case. In this case, magnetic field is quite weak. So the field line in this case are forced to move with the gas. Whatever the gas has what kind of motion, the magnetic field line have to follow it. Yeah. This is the two typical approximations we will see in the literature. Yeah. For example, in the corona, in the accretion disk corona, it is generally in this region. But within the accretion flow, it is in this region. Viscosity and MR, magnetorotational instability. So this is the viscous torque we usually or typically use in. You can see this equation in the textbook I mentioned at the beginning. We have such kind of stress. This is omega, this is the angular velocity r. This is the kinetic viscosity. So this is the stress. From this stress, we can obtain the viscous torque. This is this way, because this is the force in per unit area. So times the area, we have the torque, that radius. So all these equations you can find in the textbook. So if you cannot figure out immediately, it does not matter. The work done by the net torque is described in this equation. So this term consists of the two terms. One is the convection of the rotational energy. So this is the rotational energy. This is the convection in the radial direction. Another term, this one, is the local rate of the loss of the mechanical energy to gas. This you can see is a friction. Because of differential rotation, we have friction. So kinetic energy, some part of the kinetic energy will be converted into the thermal energy. In Chinese, 摩擦生热, right? So these are two terms. However, many studies have shown the typical viscosity we usually use in the Novikov-Stokos equation, for example. They are too small. Too small means they are not large enough to transport the angular momentum to let the black hole accretion to occur. So this is why we have to invoke anomalous viscosity. Typically, what you often see in the paper is the so-called alpha viscosity. This is first introduced by Shakura-Sunyaev. So this is the typical formula describe the anomalous viscosity. This is the stress, and this is the alpha parameter, and this is the pressure. Usually it is the gas pressure, to proportional gas pressure. So in this case, the torque and the work done by the viscosity can be described in this simple way.
So what's the physics to drive this alpha viscosity?
Yeah, this is this slide. Yeah, good much. Okay. Well, what is the physics underlying this alpha viscosity? Anomalous viscosity is just a phenomenological expression. We want to know the underlying physics. The physics is here. It is magnetorotational instability. Okay. So this instability was originally found by Chandra-Sekhar in many years ago. But This was rediscovered by these two scientists in this year. And after that, they did a lot of work, including analytical and also shearing-box numerical simulation, to intensively study this instability. This is why both of them won the Short Prize of Astronomy this year, because they think important contribution to astronomy, to black hole accretion. So what is MR? So consider a rotating accretion disk. Okay? If there is no magnetic field, so we have a so-called Reynolds criterion. So whenever this rotating disk satisfies this equation, we can show the disk is unstable. Okay? So this is already confirmed by a numerical, not numerical, a real experiment. This is done in Princeton by Feng Yuan Hot. Some of you know. So all astrophysical disks should be stable against this criterion. However, whenever we have a vertical magnetic field, and this magnetic field is well coupled with the gas. Well coupled, this is always, almost always satisfied in astrophysics, especially at least in black hole accretion, because in black hole accretion disk is the gas is at least partially ionized, so the well coupled with the magnetic field. In this case, this criterion will be changed into this one. So you can see the difference. Okay? This is called differential rotation. This means at the different radius, the specific angular velocity is different. Okay? This is exactly the case for Keplerian disk. Keplerian disk satisfies this equation. So in this case, we will have MR, magnetohydrodynamic instability. So what is the, why we have special interest to MR? This is because now it is widely accepted. MR is a mechanism of angular momentum transfer in a accretion disk. In other words, if there were no MR, we will have no black hole accretion disk. Okay. So the one consequence of this kind of instability is it can amplify magnetic field. Why? This is because whenever we have MR, we will find the accretion disk will become turbulent. So you remember, I said just now, in this case, magnetic field is not so strong. So whenever the gas becomes turbulent, the magnetic field line will also become tangled, because the magnetic field line have been controlled by the gas. So once the magnetic field line becomes tangled, so the magnetic field will be amplified. Okay? So this is one consequence of this instability. Okay? So another one is, I already mentioned, we have permeability turbulence. Okay? So in this, so once we have such kind of instability, we will have both the magnetic field amplified and also turbulence. So these two things will correspond to this kind of two stress. A magnetic field corresponds to the Maxwell stress. Turbulence corresponds to Reynolds stress. So it is this the sum of these two stresses which play the role of transport angular momentum in a accretion disk. This is a symmetrical figure why MR can occur. So this is a accretion disk. A black hole is here. So suppose we have a vertical magnetic field at the beginning. So suppose the magnetic field line is perturbed from this radius to this radius. Let's see what will happen. Okay, at this location, the rotation force, the centrifugal force, will be balanced by the gravitational force. Okay. However, when this the magnetic field line is perturbed into this radius to this location, because the whole field line is still rotated as the speed, as the angular velocity of this radius. So you can imagine when the field line is perturbed to this radius, the centrifugal force will become larger, right? And also the gravitational force in this radius will become smaller. So what will be the consequence? The perturbed fluid element will have a net force outward. This means the perturbation will grow. Right? This is why we have MR. So you have some question? Okay, that's one. I think you can feel free to ask me any questions. Okay. Huh? What? Yeah, do you understand what
I have a question.
Yeah.
So how to estimate the insulation, which resolution will be enough to resolve MRI?
Sorry,
How to resolve MRI?
Resolve MRI?
Yeah, in the simulation,
Oh,
how to estimate what kind of resolution is enough to resolve?
Oh, you asked me quite an advanced question. Well, I propose one paper to you. This is written by John Holley, maybe in 2008. So that paper is discuss this question. So briefly speaking, we have a typical wavelength for MRI. So this is the wavelength where the growth rate is maximum. MRI in this wavelength grow much fastest. So the grid of our numerical simulation must be smaller than such kind of wavelengths. This is a very rough description.
But how do we know the growth rate is correct in simulation?
Well, in practice, one way perhaps you can use a different resolution to do the simulation, compare the result to see whether they conserve or not. So this, I show you a movie of MR. This is at the beginning, we have a rotating gas tolerance. Okay. Then of course, we put magnetic field. Then we let it evolve to see what will happen. This is the cross section. Okay. So you can see it obviously becomes quite turbulent. It is not a laminar flow. This is because the turbulence, the production of the turbulence is because of MR. And also we can see accretion really begin. So another thing I think you have interest in, what's the value of alpha? Okay? This is in a very practical use. However, in this aspect, MHD numerical simulation, the result is quite diverse. Different people, different setup, different groups, they have different results. So, but in general, we summarize their result. We will find the value of the alpha usually increase with the net magnetic flux used in the numerical simulation as the initial condition. How many net magnetic flux they put in the beginning of the simulation. This will roughly determine the final value of the alpha in the simulation. It can be ranged from this value, 0.01, up to even 1, or even in some simulation result, it can be larger than 1. Okay. So now let's summarize the general picture of the black hole accretion models. So roughly speaking, we have two series models. One is cold, another one is hot. This is divided by the temperature of the accretion flow. Okay. Look at these arrows. So in this direction, this is the increase of the accretion rate. So when this is in unit of Eddington accretion rate, then low. So when this the accretion rate is larger than typically 10 to minus 2 Eddington, we will have cold accretion flow loss. In this regime, it will be in the regime of standard thin disk or Shakura-Sunyaev disk, SSD. If the accretion rate is even higher, it is higher than the Eddington accretion rate. In this case, we will have super Eddington accretion flow. Sometimes people are calling it slim disk. The first paper in this field written in this year. This is, by the way, this scientist is my advisor's advisor. So this is a super Eddington equation. Okay. So typically, for tidal disruption event, and also for ultra-luminous X-ray sources, and also a very famous X-ray binary, SS433, people usually think they are within the regime of super Eddington equation.
No, I have a question. Is for this different accretion rate, is like the same disk will evolve, go through a different stage of this, or just specify for one disk at certain
Okay, okay. You asked me a question. I will talk about it later. But this time not the next slide, but the next chapter. So wait. For standard synthesis, this is widely used at least many years ago in astrophysics. So now we believe typical quasar, AGN, save the galaxy, and also nebulous binary, the thermal or high soft state is in this regime, standard synthesis. Roughly the accretion rate is found to this one. Below this accretion rate, below 10 to minus 2 Eddington accretion rate, we will have hot accretion flow model. So if the accretion rate is very low in this regime, we will have advection-dominated accretion flow. Okay. Or some people like to call it a real, relatively inefficient accretion flow. When the accretion rate is higher than this, roughly than this value, but below this value, we will have luminous hot accretion flow. So the difference between this one and this one is in this parameter regime, it corresponds to different accretion rate. And effectively, they can produce a different luminosity. And also, their radiative efficiency is also different. I will talk about this later. For hot accretion flow, it's now recognized most of the sources, most of the centers of galaxies in our universe is in this regime, hot accretion flow. For example, some low luminosity AGN, BR-like object, and also this is the supermassive black hole in our galactic center, Sagittarius star, and also another very famous AGN, M87, and also black X-ray binary, the hard and the quiescent state. All this stuff are in this regime. Okay. This is a very general picture. Okay. I hope you have some concept. Okay. Okay, now this is the end of the chapter 1. You can ask me some short questions before I continue.
Accretion needs a magnetic field, but in your simulation, how to put a magnetic field structure?
This is relatively easy. You can just put some magnetic field, except you need to pay attention technically. The divergence of the magnetic field must be 0, so medium. And also another thing is you should not put too strong magnetic field, because MR require weak magnetic field.
For different configuration of better result.
This is another good question. This depends on what question you want to study. For example, if you study jet formation, so the initial configuration of the magnetic field does matter. It turns out if you only put a toroidal magnetic field, you know toroidal? Okay, in that case, we almost have no jet. So to produce jet, we must put at the beginning some toroidal component in this direction. But if you want to only focus on MR, for example, the initial field configuration does not matter too much. So depend on your question. Okay, let's go on. So in chapter 2, I will briefly introduce standard synthesis and slim disk. Because I suppose my role in this summer school is mainly to introduce hot accretion flow. So this chapter will be short. Okay. And also this is a quite, this is a very mature theory. So first is standard synthesis. So this is the equations to describe a black hole accretion flow. So first is mass conservation. momentum in the radial direction and momentum equation in the rotation in the toroidal direction, and also the energy equation. So this, you know, this is accretion rate. This is the height of the accretion flow, the density, radial velocity, pressure, angular velocity, Keplerian velocity. Okay. This is the specific angular momentum of the gas when they enter into the black hole horizon. This is the integral constant, because this equation is obtained by integrate the angular direction of the momentum equation. Okay. This is the integration constant. For the energy equation, this is the entropy of the gas. Okay. And this is the viscous dissipation rate or turbulent dissipation rate. This is the heating rate in the accretion disk. And this is the radiative cooling. So this equation is basically the first law of thermodynamics. Okay. This is the gradient of entropy equal to this, if you know, TdS equal to dq, dq, right? Yeah. dq means this is the heating term, this is the cooling term. Okay. So this quantity needs to be explained a little bit further. This quantity describes the radiative cooling. So for standard synthesis, we will have such kind of equation. So this is the speed of light. This is a constant. This is density. And this is the so-called radiation constant. Okay. It is corresponded to Stepan-Boltzmann constant, describing radiation. This is the temperature. This is the height of the disk. So let's see something more about the energy equation, about this one. How do we get these equations? Okay. So for thin disk, the effective optimal depth is much, much larger than 1. So in this case, from the textbook of radiative transfer, written by Viscous and Lightman, you will find such kind of equation. So you will see how we derive these equations. This describes the flux, the radiative flux along the vertical direction of the accretion flow as a function of the Z. Okay. This is the gradient of the temperature. Okay. So, of course, we should have the gradient of this flux should be equal to the dissipation rate. Okay. This is obvious. Okay. So, integrate this equation, we'll get this equation. So this one means the integration along the whole vertical direction of the thin disk. This is the dissipation rate per unit area of the thin disk. Okay. So this is why we finally get these equations. Okay. So as I emphasized before, it is very difficult for some of you to immediately understand everything, but I think you just have some concept that will be quite useful. So here is the overview of the thin disk model. For standard thin disk, the temperature is cool. The accretion disk is cool. The temperature typically is 10 to 6. So because it is cool, it is geometrically thin. Why? This is because the height of the accretion disk height is determined by the balance of the two forces. One is the gradient of the gas pressure. It is in this direction. The gas pressure is higher, then the disk will become thicker, right? It will pump up. Okay. Another force is the vertical component of the gravitational force by the central black hole. Okay. Because the central black hole must have a force to this gas. And this gravitational force must have a vertical component, which is downward. The gradient of gas pressure is upward. So the balance of these two forces will determine how thick the accretion disk will be. Okay, this is why when the temperature is low, we will have geometrically thin disk.
I have a question. So what's the mass of the disk compared with the black hole?
Okay. This depends on what kind of object you are discussing. Let's discuss AGN. This is the most right. So for low luminosity AGN, the mass of the disk can be neglected. This is a general conclusion. But for luminous AGN, for example, quasar, above beyond some certain radius, the mass of the disk will become comparable to the mass of the central black hole. So in that case, we will have gravitational instability. Okay. This is why, for example, typically for quasar, it is several hundred Schwarzschild radii. Above this, beyond this radius, the mass will become quite important, become gravitationally unstable. Another typical feature of the thin disk is the rotation is almost perfectly described by calculating the rotation. Why? This is because the radial force balance for accretion disk is three forces, you may remember. One is the gravitational force. Another one is the centrifugal force, outward. The third one is the gradient of the gas pressure. Okay. For thin disk, because the temperature is quite small, so the gradient of the gas pressure is always can be neglected compared to the other two forces. So this is why the rotation of the disk of the thin disk is always capillary. You will see for thick accretion flow, hot accretion flow, this is no longer the case. Okay. The radial velocity of the thin disk is quite small. This is another important feature. This means our accretion time scale will be quite long. And also because it is geometrically thin, and the radial velocity is quite small, so the surface density of the accretion disk is quite large. This means that it is optically thick. So once the photons are produced within this accretion flow by some various kind of physical mechanism, ramshackle and simple radiation and so on, it will collide with these electrons with the plasma many times, even absorptive and radiative, before they escape from the accretion disk. We call this case optically thick. So this is a typical feature for thin disk. So because it is optically thick, so the spectrum emitted by the accretion disk at different radii, it is perfectly described by the Planck spectrum. It is black-body spectrum. Okay. Of course, different radii, the temperature will be different. So this is why we have the so-called multi-temperature black-body spectrum. Okay. This is thin disk. And also another important feature is the radiative efficiency of the thin disk is quite high. It is typically, the value we use is 10%. This value is only a function of the black hole rotation, the spin of the black hole. When the spin of the black hole is large, this efficiency will become larger. The reason is because when the black hole is rapidly spinning, the innermost radius of the accretion disk will become closer to the black hole horizon. So you can imagine in that case, more gravitational energy will be released by the accretion disk. This is why efficiency will become higher, and vice versa. Okay. Now let's talk about again radiation. So this is the dissipation rate of the accretion disk. I described before, and this is the surface temperature of the accretion flow. So please note this equation different from the equation I showed before. This is because the temperature is different. Here I use T, but previously I use Tc. Tc means the central temperature of the accretion disk in the equatorial plane. But here the temperature T means the surface temperature, the temperature of the accretion disk at its surface. So these two values are different. Okay. So from this equation, we can get the value of the temperature as a function of the radius. Of course, it's also the function of other quantities, the accretion rate. Okay. So this is quite easy to understand. This is an algebra equation. Okay. So we immediately or easily calculate the temperature value. The spectrum emitted by such kind of temperature structure is described by, this is a emitted spectrum at H radius. Okay. At H radius, the temperature is described by TR, and the spectrum is described by the Planck of black body spectrum. Then we integrate this spectrum from the innermost stable orbit. This is the innermost edge of the accretion disk to a very large radius. We'll get the total spectrum, which is of radiation, which is this equation.
So what the R star here means? R star.
Oh, this is the star, the radius of the star. So because I directly copy this equation from the textbook. In textbook, they not talking about black hole, but a star accretion. This should be regarded replaced by the innermost stable orbit of the accretion disk. We have the famous Shakura-Sunyaev solution, which is this set of equations. Okay. Well, these equations is to resolve the accretion equations I introduced for here. However, we must make some assumption, simplification, before we can get these very simple algebra solutions. So all these assumptions are, we assume the gas pressure dominated, and also we assume alpha viscosity, and also we use Rosland opacity. Is approximated by Cramer's law. So this sense, if you are not familiar, you can look at the textbook I mentioned. Okay. So from this solution, we can see this is the surface density, the height, this is the density, this is the central temperature, this is the optical depth, this is the kinetic viscosity, the radial velocity. All these quantities can be described by algebra equation of some basic parameters like accretion rate, black hole mass, radius, and so on. F means this one. Okay, so standard synthesis model in this sense is quite simple. So this slide shows the typical spectrum emitted by a standard synthesis. So different lines correspond to different accretion rate. Okay. So this is typical multi-temperature black body spectrum. Okay. It is slightly different from the one temperature gamma spectrum. Okay. Only because the temperature at different radii is different. Okay.
So here you mean this is a spectrum by summing all the emission from the different radii.
Yeah.
Getting this
Yes.
result.
Yes. After we integrate from the innermost to the outermost radius.
Is there any transition operators?
Yes, yes. No. Well, this is only a somewhat schematic figure. So yeah, maybe we use a typical transition angle. But the inclination angle does not affect the shape of the spectrum, only affect the normalization. Okay, this slide taken from one famous paper. The first author of this paper is from Taiwan originally. Okay, this paper. You know this guy? No?
I know.
Yeah.
Yes, I know.
Yes. Okay. Some days ago, I met this guy, his advisor, in a conference in Paris. Okay. And we talked about this old work. Anyway, this work is quite important because it is a very pioneer in this field. They first used the standard synthesis model, try to fit the best spectrum at that time of AGN. Okay. So this is their fitting result. So you can see roughly it's quite good. It's quite satisfactory at that time, at least. Another important topic, which is quite hot in about 10 years ago, is how to measure the spin of the black hole. Some of you may know. So now let's briefly talk about it. How to measure the black hole spin? Because the spin is a sole function of the innermost stable circular orbit, the innermost edge of the accretion disk. So to measure the spin, we we need to measure the inner disk radius, okay, which is this one. So within this radius, there will be roughly, say, no radiation. Only beyond this radius, the accretion disk can have strong radiation. And this value is a function of black speed. This is why once we get this value, we'll have the black speed. Okay. This is the symmetrical figure. For zero black hole speed is equal to 0. The radius will be large. If the spin is equal to 1, it's quite large. You can see the ISCO, the radius of the ISCO will be much smaller. Okay? So this is a basic principle. How do we measure the ISCO, the value of the ISCO? First, let's consider a star. Okay, this is a very typical star. So for this star, suppose the radius of the star is r. The luminosity will be described as this one. This is the flux. This can be observed by our telescope, right? So if we also, this is the surface, the area of this star, okay, this equation. The solid angle we can obtain from this equation. This is described this equation. So once this one we can measure, and this temperature we can also measure by the spectrum of this star. So once we measure all these quantities from the distance d, we can obtain the value of the radius of the star. You understand? This is okay. This can be measured. This can be measured, and once we know this d, we will have r. Okay. This is how do we measure the radius of the star. So this principle can be applied to a accretion disk. The only difference is now the accretion disk is only symmetric. It is not spherically symmetric. So in this case, we have to introduce additional parameter, which is the inclination angle. Okay. So in this case, we have to measure the inclination angle in some other different way. Typically, we can do it by measuring the period of the binary star. Okay. One is black hole, another one is the companion star. So we can obtain this inclination angle. Then we can obtain this value. This is how we measure black hole speed. So technically, to measure black hole speed require some other things. First one is the spectrum of the accretion disk must be dominated by the accretion disk component, should not be contaminated by, for example, hot X-ray and so on. Because hot X-ray, as I talk later, it will be produced by some other stuff, corona, not the pure accretion disk. So this means we have to look for the standard high soft state of black hole X-ray binary, very clean spectrum. And also the theoretical profile of the disk, we use the standard. This is Novikov sum. This is you can regard the same with suppressed value in the GR version. The same disk, we must require h over r must be smaller than this value. Otherwise, the disk will be too thick. So the solutions we just described will be not valid. So this is another requirement. Then we also need to some accurate estimate of the black hole mass, distance, and inclination angle, as I mentioned before. So once we have good measurement to these quantities, we can have a good measurement to the ISCO value. Of course, another technical complication is spectral hardening. I think I can skip this part, spectral hardening. This is scattering of the photons with electrons. Once we, in this case, the spectrum will deviate from the standard Planck spectrum, but become harder. This is why we call the spectrum hardness. Okay. If it is purely absorption, the photons absorbed by electron are radiated, this will give a perfect Planck spectrum. Okay. Then let's talk about the thermal and viscous stability of the thin disk. So this is a very commonly used diagram in black hole accretion. So the y-axis can be effective temperature or accretion rate. And x-axis is the surface density accretion disk. So we solve for these two quantities. I change the value, for example, of the accretion rate. We will get such kind of S-shaped curve. Okay. So if the accretion rate is low, of course, it will correspond to this branch. With the increase of accretion rate, the accretion disk will enter into this branch, and then finally this slim disk branch. This is the super Eddington accretion branch. Okay. A very simple way to judge this instability is just to look at the slope of this curve. If this slope is positive, we can show it will be stable. But if this slope is negative, like in this branch, we can show it will be unstable. So you can look at the textbook for some details. This is not so easy to explain in a simple form. Okay. This I just give you some general picture. So for standard synthesis, you can see if the accretion rate is not so high, it will be stable. However, in this regime, this is also typical for standard synthesis. It will be unstable, suddenly unstable. So, and if they enter into slim disk regime, they will become stable. Okay. So this regime is really is a very serious challenge to black hole accretion theory. This is because observationally, we already observed many sources is in this region. From the observation, we can see directly they are quite stable. Even their variability in terms of the IMS value is quite small. So, but theoretically, we predict they should be unstable. So what is the matter? This is the topic of hot study in the previous years. Unfortunately, this problem still have not been resolved. Okay. Oh yes, this slide explains this series. Thermal instability of thin disk is still an open issue. Observation to some softer state of F3 binary, so they are quite stable. Okay. This is, you can look at one paper by Tom Jelinski in 2005, maybe. Yeah. So to solve this problem, people recently did some radiative MHD numerical simulation. Okay. Unfortunately, different people obtained a different result. So one group, this group, they found that the accretion disk is thermally stable. So this is quite good. This is good news because this means theory is consistent with observation. Unfortunately, several years later, some other people, they did a more careful study using better numerical scheme. They found that they are thermally unstable. So anyway, this problem is still unsolved today. Okay. So far I described some success of the standard thin disk model, but I should emphasize this is not the final story. Actually, now we have many problems for the thin disk model when we try to explain observation using this theory. So here's some lists. One is the microlensing result. Microlensing means there is a black hole accretion disk. And between this black hole accretion disk and the observer, there will be a galaxy. The galaxy, of course, composed of many stars. And these stars will have motion. The radiation coming from the accretion disk will pass through these stars. And when the light is close to the star enough, we'll have a general relativity effect, which means the light will be bent somewhat. So anyway, we will have some variability because this microlensing. Using this technique, we can measure the size of the accretion disk. It turns out the size measured by this observation is typically a factor of 4 larger than theoretical prediction. So this is one serious problem. But you can, if you check the website about 1 month ago, we put a paper in the archive to try to explain this result using some updated accretion disk model. We use the wind. Wind is a topic I will discuss in chapter 5. Another problem is it underpredicts the UV spectrum of AGN. And also, this is the spectrum index between FUV, this is, and this is black mass space. It's also not considered a model. For some detail, we can check this paper. Another one is it is hard to explain the simultaneous variability at different wavelengths. And that's one. And also, finally, wind must exist. But in the standard synthesis theory, we cannot take into account the wind. It turns out the wind is very, very strong, as I will tell you later. Okay. So all these things are the problems we now face with standard synthesis model. Even the fitting of the optical UV spectrum is the so-called big blue bump, and I show you some American 1989 paper. Now people recognize the fit is not perfect. There will be a very strong conflict with observation. Okay, now we talk about the disk corona model, because this kind of model is frequently mentioned in the literature, especially in X-ray observation paper. Many observers like to use this phenomenological description or X-ray radiation. They usually say, okay, the X-ray is emitted by the corona. What is corona? Okay. The initial motivation for this disk corona model is from this sun, solar physics. Because we know in our sun, we have a photosphere. We also have a chromosphere. Then above it, we have a solar corona. So this is the origin of the corona concept. The corona of the sun, the temperature is much, much higher than the chromosphere. Okay. So by analogy with the sun, the structure of the sun, people proposed, maybe in 1970s, proposed this corona model. Okay. The purpose of this model is try to explain the origin of X-ray radiation. This is because the standard synthesis model cannot self-consistently produce any X-ray radiation because the temperature is too low. It can only reach to optical or at most UV, cannot reach to X-ray. Okay. This is the motivation, and the basic picture is my analogy with the solar corona. What is the formation mechanism? The formation mechanism, the corona, is also by analogy with the solar corona. Okay.
You're talking about AGN, right?
Hmm?
For X-ray binaries, the temperatures get high enough to produce X-rays.
Well, I think it is still hard to explain hard X-ray.
Hard X-rays,
Yeah.
that's right.
Yeah.
Okay.
But X-rays, extend to quite a large range energy band. So I think it's not satisfactory if we can only explain soft X-ray. That's not obviously not enough.
Right.
Okay, what is the formation mechanism of the corona? So this is, again, we have to invoke magnetic field. So within this accretion disk, as I said before, we have a turbulent magnetic field. And this magnetic field will have a so-called Park instability. If you are familiar with the solar physics, you know Park instability. This is basically when they have some magnetic flux, magnetic cube within the accretion disk or within the sun. Okay. This magnetic cube, they will have a buoyant force. So this means this magnetic tube will emerge from the accretion disk into this corona region. And once this magnetic field emerges out, the magnetic field line above this accretion disk become quite strong. And also because the accretion disk is quite turbulent, so you can imagine the magnetic field line above this disk will also become turbulent. Then the consequence will be we will have very strong magnetic reconnection. Okay. So magnetic reconnection means magnetic field line with different polarity Once they become close enough, they will reconnect. So the magnetic energy will be converted into the solar energy. This is why the corona region above the disk will be heated by this magnetic reconnection process. Okay. The temperature of the corona, they argue, can be high enough to explain the hot X-ray radiation. This is the basic picture. Okay. Unfortunately, this picture, in recent years, because of the rapid development of numerical simulation, including radiative, three-dimensional MHD numerical simulation, quite complicated, quite advanced, they began to touch this phenomenological model to see whether it is correct or not. Unfortunately, the result is, so far, they found this picture seems to be not work. Okay. Specifically, they found that the temperature of the corona is not high enough, and that the matter within the corona is not enough. Anyway, they cannot produce, cannot explain or observe strong X-ray radiation. Can only explain some very weak X-ray radiation. This is the current situation. Okay.
So if that corona exists in the disk, so that means also will be drive the strong wind on the surface of
Why?
the disk.
Why is it so?
Like solar.
Solar wind.
Yeah.
Yes, yes, you are true. Well, this is again I will talk about in chapter 5. The accretion disk. But your idea is actually quite advanced because currently the popular model to explain the wind from thin disk is by radiation line force. The output in some observatory when I try to study ideas similar to what you proposed. So that's the biomagnetic line to see whether it can work or not. Yeah. We only got some initial result. We found it came. Yeah.
So I also wondering about the corona, because you want to get a hot X-ray, so that means you need to have, the gas must be very in high temperature.
Yeah.
And those gas heating will come from the reconnection of the magnetic field line to drive such high temperature.
Yeah.
I see.
Yeah.
But in simulation, can people really simulate this in self-consistent way?
Well,
Is it actually radiation and reconnecting all together?
radiation, no problem. People can also do very exact, precise radiative transfer simulation. But the magnetic reconnection is a problem because intrinsically reconnection cannot be described by MHD theory. It is intrinsically a kinetic thing. Right? We have to use a particle theory rather than fluid theory. So in this case, people have to make some assumption, approximation. But generally, people think a result obtained is reliable. Yeah, this is the simulation I mentioned. So if people have interest, you can look at this paper. Okay. So this is Yan Feijiang, Chinese. This is Jim Stone, now the chair of the astrophysics department of Princeton University. And this was his postdoc. Okay. So this is the result was just already explained. So basically, they found they do careful radiative energy simulation of corona, and they turn out the corona not strong enough to explain observations. I think we can have a rest.
Yeah.
Yeah.
Need some more questions?
Yeah, before, yeah.
If there's no question, then let's have a break.
Okay, let's come back at 30. Half?
The scheduled time is 10 to 4 for the next slot.
Okay.
If we finish earlier, then maybe we can have 10 minutes earlier. So let's come back at 3:40. Okay?
Okay?
Yep.
Okay.
Okay.